Ask Python whether 3 is in the list 1, 2, 3, and it answers true. Wrap that same list inside another list, ask again, and it answers false. Same 3, same values, one extra pair of brackets. Today, recursion goes to work on lists of lists, flattening them, searching inside them, and settling when recursion, not a loop, is the right tool. Suppose every element of the input list is itself a list. Here, the outer list has exactly 3 elements, the list 1, 2, the list 3, 4, and the list 9, 8, 7. Flattening removes any semblance of sublists. Every integer moves up to the top level in order, giving 1, 2, 3, 4, 9, 8, 7. One assumption keeps the problem clean, no lists within lists within lists. Just a list whose elements are lists of integers, one level of nesting. That makes it a perfect fit for the pattern from last lecture. Peel off the first element, recurse on the rest. Here is flatten. L is a list whose elements are lists of integers, and the goal is one list containing all those integers in the same order. Start with the smallest input, the length 1 case, a list holding a single inner list, double square brackets around the 1. To flatten it, return L at index 0. The element at index 0 is the inner list itself, and that inner list is already the flattened answer. So the base case reads, if the length of L is equal to 1, return L at index 0. The recursive step reuses the peeling pattern with one twist. The first element is already a list, so the way to combine it is concatenation. Return L at index 0 plus flatten of L from index 1 onward. Concatenating two lists produces one big list with all their elements, exactly what flattening means. Watch it run on the bigger test. The first element peeled off is the list 1, 2. We trust the recursive call to flatten the remainder. The lists 3, 4, and 9, 8, 7 into 3, 4, 9, 8, 7. Concatenating 1, 2 with 3, 4, 9, 8, 7 yields 1, 2, 3, 4, 9, 8, 7. And on the one element test, flatten of the list holding just the list 1 returns that inner list unchanged. Both printed results confirm it. The list containing 1 and the list 1, 2, 3, 4, 9, 8, 7. Your turn. A variation on membership. The list has the same shape, and the job is a recursive function that reports whether an element hides inside the sublists. First, see why the plain-in operator falls short. 3 in the list 1, 2, 3 is true, but 3 in the list containing the list 1, 2, 3 is false. At the top level, in compares 3 against the inner list itself, a top-level equality check. And it never looks inside, so the ground rules you may use in to test whether the element sits inside one particular sublist, but not to search the nesting for you. That part is the recursion's job. The function is called in lists of list, and it takes the list of lists L and the element E. Build the answer from the same two cases. In the one-element case, the length of L is equal to 1, so L holds exactly one inner list. L at index 0 is that inner list, and the answer is whether E is in L at index 0. There is no need to write an if that returns true and an else that returns false. E in L at index 0 already evaluates to a Boolean, so return it directly. Otherwise, the list has several sublists. Check the first. If E is in L at index 0, return true and stop. The tempting else, return false, would be wrong. Missing the first sublist proves nothing about the rest. Instead, the else recurses. Return in list of L from index 1 onward with the same element E. Now trace the test. The sublist 1, 2, 3, 4, and 5, 6, 7. Searching for 3. 3 is not in 1, 2, so recurse on the remainder. 3 is in 3, 4, so that call returns true, and true flows back out. Searching for 0, 0 misses 1, 2 misses 3, 4, and the final call is the one-element case where 0 in 5, 6, 7 evaluates to false, so the whole call returns false exactly as printed. One optional refinement, an extra base case. If the length of L is equal to 0, return false, because an empty list contains nothing. Most of the examples so far are just as easy to write with a loop, so the honest question is what recursion buys. The answer echoes while loops. Try to code a little game with only if and else, and you end up with a pile of nested branches, because without a loop, you cannot know how many turns the game will run. The same wall appears with nested lists. With for loops, you would say, for each element of L, handle it directly if it is not a list. If it is a list, write another loop over its elements. Inside that loop, the same test returns, demanding a third loop, then a fourth. Your nesting depth is frozen at whatever you typed, while the data makes no such promise. A while loop can chip away at it. While this element's type is a list, keep drilling, but that row turns really verbose. Recursion is how we deal with lists within lists within lists, and more broadly, with any structure whose depth is unknown. A file system is the classic case. Folders holding files and more folders, nested however deep the user happened to make them. Sets of operations from last lecture behave the same way. So does the Scooby-Doo gang hunting a culprit through a mansion. Rooms with doors that open into rooms with more doors, and nobody knows how many doors stand before the final room. One recursive function, search this room, then recurse through each door, handles every depth with no extra code. Two problems, one pattern. Flatten peels off the first element, itself a list, and concatenate it with the flattened remainder. Its base case simply returns the single inner list. The membership check peels off the first sublist, tests it within, and recurses on the rest when the test misses. Each function is a base case plus a recursive step, nothing more. The larger lesson, nested for loops, force you to hard-code the nesting depth in advance, while recursion re-asks the same question of a smaller structure until it bottoms out. When data nests to unknown depths, sublists, folders, rooms behind doors, reach for recursion. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.